All right, let's go ahead and get started. Let me get the sign-in sheet passed around. Again, you all have a homework assignment due today, so if you have not turned that in, right here, did you all enjoy the triangular beam problem? Let me say this real quick. So the purpose of that triangular beam problem was to present you a challenge regarding the stress block formula. And you know, some of you probably got it right, some of you probably got it wrong, that's fine. But the point is that I really wanted you to be familiar with the Whitney stress block approach. Because when we do things like T-beams or doubly reinforced beams, you really need to be comfortable with that. And my thought is, now I'll challenge you with this, and you get it right, great. If you get it wrong, you'll know where you did wrong. So when you start to see things like T-beams and what have you, that stuff comes second nature. And it's one of the ways to really learn it is to just do something pretty difficult. Now, I'm sure I'm going to score a lot of points today with this, but now that you've turned in this homework assignment, I have another one for you. But you should have known that because that was on the schedule. But keep in mind, I've given you a fair amount of time on this one. This is not due next Wednesday. It's due the following Monday. So you've got a lot of time on this one, okay? You stole the words right out of my mouth, Mr. Pava. Again, make sure you're not waiting till the last minute. This homework is not that bad if you don't wait, but there are a couple of design problems on here that you'll want to take your time with. In fact, other than the first problem, it's all design. All right, so I'm just going to pass these out. If you already grabbed one, just keep the packet passing down the line. Somebody already grabbed one. I think we might have an extra one that needs to go back here or something, so just help me out with that. Now, I know that some of you are probably looking at this example and thinking this is the example that doesn't seem to want to die and move on. But I do want to show you all something real quick, and we might have a little fun with it just so we can discover some things. For this problem, we needed to design a 22-foot long beam, and we needed to look at using 4 KSI concrete, 60 KSI steel. Here was our loads, a dB ratio of 1.5, and from that we generated a design, right? And if you remember, let me pull this up. Let me zoom in here a little bit. Can you all read that? Is that good? Okay, so 4 KSI concrete, 60 KSI steel. Our beam dimensions that we came up with when it was all said and done, if I remember, was 14 inches wide and effective depth of 21. So that yielded a height of 24. And then we chose, was it 3 number 11s or 3 number 10s? I can't remember. 10s. 3 number 10s, and this was 3.79. So based on that, we were able to do these calculations. Now what I've created here is an Excel sheet that basically, based on changing a given value, it'll recompute everything. The two things I want you to pay attention to are this, which is our loads, MU, that's how much the beam is experiencing, and this PMN, that's how much it can withstand before it will fail. Now there's a couple interesting things that can happen here. For instance, let me back up. So the reason I created this is I want to just take a little bit of time and look at the sensitivity of some of these parameters. Like, for instance, let's take FC prime. Remember, that's your compressive strength of your concrete mix. What if I double that? How does it really change the answer? You see what I mean? If I double the compressive strength of the concrete, you think it's going to double this? You tell me. What do you think? It'll go up, but will it go up significantly? Well, let's see. If I change that 4 to 8, that's all it does. Keep in mind, it changes your beta 1. It ultimately changes all of your strains and your A values. My point is, let me ask you this. Does the strength of the concrete in the overall scheme of things, does it really matter? Like, does it? I mean, but how much does it matter? I mean, I'm talking about scale. I want you all to understand the big picture. You see what I mean? This isn't really that big of a deal, okay? What about this? What about, okay, what if I go back? What if I make the beam deeper? What if I make the beam like 27 inches deep? That changes things quite a bit, doesn't it? But it also creates a heavier beam. And at the same thing, it raises your capacity substantially, but it doesn't quite raise your loads as much. Because of that, we don't really have a very efficient beam. See what I mean? All right, what if we do, now watch this. Okay, what if we go Steelers? I just wanted it to stand out. I am a Steelers fan, but okay, we'll skip the NFL discussion for later. All right, what if I take the area of steel though and just increase it slightly? What if I do like 4.0? Okay, that starts to affect things a little more substantial. Like it was 3.79. What if I double it? Okay, if I double the area of the steel without changing the beam dimensions at all, that really substantially changes the strength. See, that's what happens when you zoom in. You cut off some of the cells. If I double this steel area, this capacity went from like 300 to 400. It went up substantially. And all I did was place a few more bars in the beam. Think about that, okay? Instead of, doubling the strength of the concrete, all I did was place a few more bars and the beam strength changed substantially. My point is that your bar selection has a significant impact on the strength of the beam, more so than things like the mix of the concrete. And that's just something I kind of wanted to discuss right at the beginning so you all kind of had a bigger picture aspect. Let me get back. This was like 3.79. A couple other parameters, like if I change the beam width, like if I make that an extra 6 inches wide, that really doesn't change things very much. So you can go around, you all can make a sheet like this on your own. I'm not giving you one because I want you all to understand these calcs and do them on your own. But it's almost worthwhile to just kind of understand the sensitivity of some of these parameters. Things like the concrete compressive strength, it matters, but not substantially. Things like the depth, because that's where you get bending strength, and things like the area of steel, those are the values that actually have more impact on it than the strength of the concrete. Just something to bring up and something to, food for thought for what's coming next, which is selecting reinforcement for a given cross-section. I thought it was a valuable discussion for what comes next. Everybody all right with this? Anybody have any questions? Again, you can have fun with this and just sort of play around with changing different values, like what if the beam got longer, what if the loads changed, and what have you. So, one thing I will point out on your homework that you got today, this beam that you had to design was simply supported, uniformly distributed load. One of the problems on your homework has simply supported beams, but it has point loads and what have you. So, goodness, you have to do some structural analysis. Oh no, moment diagrams. I know you all know how to do that because, at least those of you who had me, no arrows, right? Tons of arrows. All right, inside jokes. All right. Okay, so real quick, let me go back and review this, and we'll take our time with this discussion of known cross-sections. So the design problem I'm proposing to you now is, unlike example 5, where we had to start completely from scratch and didn't have a clue what the beam looked like, here we have a problem where we know what the beam cross-section looks like. Anybody that's ever done any work with precasting or pre-stress knows that those beams, they are what they are. I mean, the sizes are pretty well defined. A lot of times if you rent concrete formwork, you're renting it in certain even increments. The point is that it's not that uncommon for a structural engineer to be given a beam size or to know what the beam size needs to be, and all they need to do is select the appropriate reinforcement that goes into that. A common pre-stressed concrete problem is, given a cross-section, figure out how many strands need to go in that beam or how many bars need to go in that beam and what have you. Excuse me. So what we're going to do is focus on that. And one thing I will say is, because we already know what the beam cross-section looks like, the design process is easier. It's much easier than what we did last time. I promise you that, okay? I promise. All right? Now, the big difference is in how we approach a problem like this is row. Because before, in example 5, we were using that 0.18 FC prime over Fy. We're using that because we've got to make a starting guess. I mean, in that example 5, we didn't have a clue what that beam looked like. So we didn't know what the reinforcement was going to be, what it should be. We just needed a good value for design purposes. Here, however, if you're in beam design mode and you know what the beam looks like, you can define Mn as a function of your beam dimensions and your material quantities. The only thing that you need is rho, okay? So you look at that expression, you go, well, I could just solve that expression and just calculate rho accordingly. So take this expression, do a little bit of algebra, rewrite it a little bit, and it's funny how that starts to look a little bit like a quadratic equation, right? Pretty simple. So take this quadratic equation and say, all right, negative b plus or minus the square root of b squared minus 4ac all over 2a. Y'all remember that? I know you've used it. Oh, come on. It better sound familiar. Goodness. I believe you all are messing with me. All right. Take this equation, solve, you get 2 values for rho. It's a quadratic. Now, one of those values is only one of those solutions is going to yield a value that we can use for the purposes of design. So going from here to here is just taking the quadratic equation and solving for rho. Okay? Everybody all right with that? All right. So here's your procedure for design. Number 1, we've got to compute our factored moments, which that's, bless you, we don't need to go through and do any design iterations because unlike example 5 where we just had to guess what the beam looked like, here we already know what the beam looks like. So there's no assumptions or iterations for MU. We just look at the beam and calculate its moment. That's it. All right. Now we still have to assume a phi value of 0.9 because we don't know what the strain in the steel is going to be because we don't know what the steel is. We haven't picked it out yet. So assume a phi value of 0.9, calculate an Mn required. Using that Mn required, we can calculate a rho for design purposes. All right? Using that rho, AS times, or rho times B times D will give us the required area of steel, and we go through the same process. Pick a pattern of reinforcement, and then analyze it to verify that assumption of phi, and make sure that we have appropriate strain in our steel and ACI requirements on minimum reinforcement. And that's it. Promise you it's pretty simple. Everybody good? Okay, so here's the beam that we're going to design. I made it a little easier on you because I just gave you the moment, okay? Moment's 160 foot kips. So we've got the beam dimensions. The beam is 16 inches wide. It's 24 inches tall. Its effective depth is 21 inches. And all we need to do is select the amount of steel that goes into this beam, okay? Everybody good? All right. All right. Let me open up a little notebook. So I promise we're done with example 5. I'll never bring it up again. Well, I don't know about never bringing it up again, but we won't do any calculations with it. Hold on. All right. Okay. Oh. Okay. All right. So let's start off with listing some of the parameters of the problem. So I'll say material values. Okay, what's FC prime and Fy? FC prime is what? 3 KSI. So just from that quantity right there, what other material-related value for the concrete can you tell me? We know FC prime, and that tells us what about the concrete? There you go. It tells us that beta 1 is 0.85. Exactly right. Make sense? We also have that Fy is what? 60 what? There we go. Again, make sure that you're consistent with that. Let's also write some of the beam geometry. So B is what? And D is, do we need H? We'll go ahead and write it down, but will we need it? We won't need it. Why? Why won't we need it? What would we use H for in this problem? We need H to calculate the beam's what? Well, we won't need moment of inertia. It's self-weight. We don't need to worry about self-weight, though, because we were given a moment. So we don't need it. Now, what's the area of steel? We got to find it. So the area of steel is, we don't know. Okay. So I'm going to go through that step-by-step procedure so that you all understand how we're going through this. So what's step one of that procedure? Compute the factored moments. So we'll say step one, compute MU. Now for this problem, MU is given. And I'm going to underline that. MU is given. So MU is what? Simple, right? Now, if it wasn't given, what would you need to do? Do a little bit of structural analysis, right? You got to do the analysis to figure out what the moments are. Draw a shear diagram, draw a moment diagram. Fun stuff, isn't it? I can see you're having a hard time containing your excitement over the entire thing. If it's simply supported. What's that? We'll see. Put, you know, like 8 hinges in it and triangular loads. Fixed couple moments. You know, make it indeterminate while I'm at it. You know. There you go. Do a little bit of matrix analysis. There we go. Do a little bit of finite elements on it. All right. What's step 2? Let's get back to this. What's step 2? We need to compute a required MN. Now, in order to do that, what do I first need to do in order to compute MN? Assume, okay, right there. Okay, so I'm going to, in, red letters, I'm going to assume a phi of 0.9, okay? So my point of marking that is I then need to go back and check that assumption to see whether or not that is valid, okay? Most cases it will be, but if you don't check, you won't know. So therefore, I can compute a nominal required moment of mu divided by phi, which is 160 foot-kips divided by 0.9. Now, in the interest of what's coming next, because I'm going to take this moment and use it with FC primes and FYs that are in KSI, I'm going to convert this into, inch kips by multiplying accordingly, right? So you plug and chug, you take 160 times 12 and then divide it by 0.9. you should get about 2133.3 inch kips. Okay. How are we feeling? So again, make sure we understand the process. So given this beam where we know the geometry, our goal is to determine how much reinforcement needs to go inside that beam. Now, we know what moment is being applied to the beam. We use that moment that was factored to determine what is our required nominal moment capacity. Keep in mind, this is not the strength of the beam. This is how much strength we need in the beam. We don't know what the strength of the beam is because we don't know how much steel is in the beam. Make sense? All right. So, step 3, compute what? Required rho, our reinforcement ratio. Now, this one is a little more involved, so I might have to stretch this one out a little bit. So rho required is, let's see, 0.85 FC prime over Fy. This is a long one, I know. So 1 minus, and then we have 1 minus a fraction. We're going to take the square root of all of this. So 0.85 FC prime BD squared. On the top is 2MN. Maybe I should put 2MN required. We take the square root of all of that. What do we think? So plug and chug, 0.85 times what? 3 KSI over 60 KSI, 1 minus 1 minus. Keep in mind, there's 2 1 minuses, okay? All right. There's 2 of those. MN required. That's MN required. But there are 2 1 minuses. I'm not pulling like a Marco Rubio and just saying the same thing over and over again. Nobody follows politics. That was bad. But that was funny. All right. 0.85 on the bottom times 3 KSI times, what's B? 16 inches times 24 inches squared. Got to extend that out a little bit. Is it 20? No, you're right. It is 21. I have 21 written, and I just wrote 24. You are correct. And that's 2 times what goes on top? 2133.3 inch kips. Now, this is a long calculation, so instead of me going just plug and chug and here's the answer, you're going to tell me what the answer is. Say it again. So 0.0053, what, 8? Is that fine? I want somebody to verify that. That's right. All right. That's long, but it's plug and chug. It shouldn't be that bad, especially with your Casios. You should be able to just plug that in. Okay. What are the units? There are no units. That's exactly right. Because on the outside of the brackets, we're taking 3 KSI over 60 KSI. The KSIs cancel. And then inside, we're taking inch kips on the top. On the bottom, what do we have? KSI times square inches. That's just kips. Kips times inches, so it's inch kips over inch kips. Make sense? All right. How are we feeling? So far, so good? All right. You want me to leave it up here, or you all good? I will leave it up here. Well, we've still got a couple writing. So.
That's row required right there.
Yeah. That's the required row for this beam. How are we doing? Good? All right. Am I good to move on? So, next page. All right. Step 4. What are we doing step 4? Compute required AS. So AS required, how do we do that? Row BD. So that's 0.538, then times what, 16 and 21? All right, plug and chug, and that gives you, that one's a simple one, 1.808 inches squared. How we doing? All right. What's step 5? That table's probably way longer than it needs to be. Bar size, number, bars, minimum, beam width. Way bigger than it needs to be. Okay. So, this is where y'all use that beam design chart, right? Okay. So, let's keep this straightforward. Let's start off. Is there any viable number 3 options, really? Okay. What about number 4? I know there's a lot of number 4s, but you want to go ahead and start with that just to have something to put on the board? What's that? Well, I am. So, yeah. Okay. 3/8. Okay, we'll see where we're at. All right, so number 4. Let's just go through the process and see what happens. All right, how many number 4 bars must we place inside this beam in order to meet our steel requirement? 10. So you put 10 number bars in this beam because the area of steel is what? Okay. Now, your minimum beam width based on 10 number 4s is what? Remember, that's the table on the bottom. If you've got 10 number 4 bars, okay, well, all right, see that? Okay, what'd you do? Okay, hold on. So let's walk that out. Okay, so 15.8 inches for 8 bars, and then so plus 2 times 1.5 inches equals 18.8 inches. See, okay, that might happen, so I wanted you to have that down there, okay? Everybody all right with that? Now, what is the beam width for this beam? What is B? 16. So that means that this option is no good. Okay, now let's do number 5s. How many number 5s must we select? All right. Okay. You picked that because there is a reinforcement pattern. This reinforcement pattern will yield an area of what? 1.84. What's the minimum beam width? 13.4 inches. So that means that we are... All right, let's keep going. What about number 6s? How many number 6s? Okay. And that is, what's that again? Minimum beam width? $11.8. I have 12.3. 12.3? So, right off the bat, before I start doing any more writing, which option should I use? The one in the middle, right? So, that's just what I got right off the bat. Now, because that's a good question. So these lower two are the only ones that will work according to beam spacing requirements. Of these two, this one would be the advantageous one because I'm using less steel. Okay? This one, we need like 1.81 square inches. This is 1.84, so we're meeting our requirements without having to spend more money on more steel. Okay? Now, let me see if you don't mind, can I see a beam design chart? Let me see. So somebody was saying, you were saying like what, number 8s or something? What number 8 option? 3 number 8s? That's 2.35 square inches. That's a good point. I mean, that's a good point overall, but not for this problem. Well, okay, you're actually making a good point that, you know, that is worth considering. That being said, if this beam is going to be repeated 600 times in a building, that could be more money that you have to spend. And it's worth considering. Yes? I wouldn't risk it. I wouldn't risk it. I mean, that's just me. I wouldn't do it. Now, I'll say this. There's actually probably a little bit of rounding that goes into those tables anyways. Those tables, I think, were generated by an Excel sheet that's actually doing the pi times whatever. What I would do is take just the single rounded bar dimensions and multiply them by their integer values. Because of that, 3 number 7s might actually be a little larger. It's a little close for comfort, though, for where we're at right now. What's that? But if that was a bridge and your grandma was going to be on it, would you sleep well at night? Yeah, maybe I should have. Do you like your grandma? Goodness. All right. I don't really want to get into a discussion of population control and reinforced concrete design. I'd rather just talk about beams and rebar if it's all right. All right, so I propose to you that therefore let's draw this out. So I have a beam that is 16 inches wide. Well,
So you're gonna have like 2.5 inches between your rebars?
okay. The rebars are, but they're only this big. Bar spacing is usually either a bar or, but we're talking about bars that are only this big, so they're tiny. We're only talking about number 5s. Keep in mind, a number 5, its diameter is 5/8 of an inch. So.
It's a question about concrete. It's not about this comment.
Okay, all right. Oh, hold on. Let me clean this up a little bit. All right. And then we're going to put 6 bars. 1, 2, 3, 6 bars. Number of, that's a good question. All right, number of bars, 6 bars. 6 bars that are number 5s. So maybe I'll write it out. 6 number 5 bars. AS is 1.84 inches squared. The total depth, or the effective depth of the beam, is 21 inches. So I propose to you that this is my, I'm being lazy when I write, let me clean that up a little bit, that this is my trial design. Okay, why is it a trial design? What assumption do we need to verify? I assume that phi was 0.9. How do I verify that assumption? I have to go through, I can compute Mn pretty easily, ASFYD minus A over 2. I then have to calculate the neutral axis depth C, calculate the strain in the steel, and the strain in the steel will tell me what phi is, right?
So we assume this at the beginning.
Yes.
We do a lot of work after that.
Yes.
Our assumption is wrong.
Yeah.
Assume we can do it all over again.
That's a good question. No. What I would say is this, is that you need to make some adjustments to your design. For a problem like this, there is only one value that we would adjust, and it would be what? What's the only thing we're adjusting in this entire problem? The steel, the amount of steel. So if your beam is too weak, put more steel into it.
So you would have to change the row required, MN required.
No, don't go back and do all of that. Just choose the next increment of steel and analyze it accordingly. Don't go back to step 1, because you're not. I mean, you're not going to change the formula. You see what I mean? If you're not going to change the formula, you're not going to change your row required. I'll say this: you're going to have. There's less of a chance that you're going to do much iteration on a problem like this, as opposed to a problem like example 5, because with that problem, you're just coming up with the beam dimensions and guessing almost. All right, so remaining steps for this problem are to compute Mn, compute the strain in the steel to get phi, and assess your problem, right? That's basically example 4, right? I propose you all can do that on your own. And I'm going to let you all do that part on your own. So if you want something to write, you could put remaining steps. We have to calculate Mn. We have to calculate the strain in the steel. Oh, minus. to get what our phi value is, and you all can do that on your own. And also I guess I should put AS minimum. And does the strain in the steel, is it greater than or equal to 0.004? You all should be able to do that on your own, though. Do you need me to do that? I mean, that's example 4. The strain in the steel, D minus C over C.
I couldn't see what that.
Well, I know, but that's in your slides, so.
If I was given this problem on homework, since it already has like beams punching out, it shows the 3, I wouldn't have, like I would assume that I would have to regardless. So how do we know to not choose?
That's a good question, and I would argue that the diagram may be a little misleading. Usually what I do is I'll draw like a rectangle, and then instead of those 3 bars, I just put a line and say like pick the amount of steel that goes here. I understand that. That probably is a little misleading. Really what the intent of the problem is just put the steel there, figure out how much needs to go there. That's a good question. You won't have to worry about that on exam day.
So for rebar spacing, would you just take the minimum cover distance and then distribute each one for the row?
Well, yeah, I would essentially, yeah. Because keep in mind that when you do this minimum beam width calculation, this minimum beam width calculation is assuming 1.5 inch cover, it's assuming number 3 stirrups, and it's assuming that you're spacing those rebar together as close as humanly possible to meet that cover requirement. So my point is, if your beam's wider than that, you're right. Just 1.5 inch cover, number 3 stirrups, and just space them evenly. You wouldn't lump them all over to one side or what have you. How are we feeling? Any questions? Now, I know you all don't have the handout for what's coming next, but I at least just want to plant the idea in your head, the concept of slab design. But does anybody need me to leave this? Sorry, leave this up? All right. Okay. I just realized. Oh no, I did pass the sign sheet around. Okay. I want to talk a little bit about one-way slab design, just so you all have the idea of what it is. Because here's my point: a one-way slab design and a beam that where the dimensions are known, they're actually really similar problems from a calculation standpoint. Okay, and you'll see why here in a little bit. I'll give you these slides next time, but I think you'll see the known cross-section problem and a slab design problem are arguably the same thing. Now, what I'm getting at is there's more to a floor system than just beams. There's also the slab, the floor system that we're actually standing on. We're not standing on beams. I mean, this is a slab on grade, but if we're on the second floor, we're standing on a floor system comprised of beams and slabs. Okay? Make sense? Now, I say one-way slabs. That might be the first question is, what the heck do you mean by a one-way slab? A one-way slab is assumed to bend one way, okay? So if I have, let's say, a beam, and I have a beam and a slab between it, I just assume that the slab bends like that. That's one-way slab design, okay? Now that's one-way slab design. Two-way slab design is if you assume that the beam bends or the slab bends in both directions, if it bends this way and that way. Now, there are advantages to doing that. You can significantly save on the cost of a floor system because your resulting slab can be thinner. Typically, two-way slabs are stronger, so they can be thinner. Your reinforcement pattern can be a little more regularized because you end up getting like a grid-like spacing and it comes out pretty nice. The problem is two-way slabs are pretty tough to analyze, at least when you're first learning it, so we'll start off just with one-way slabs. There actually are some two-way slabs on campus If you go to Drinko and you look at those floor systems, they're actually two-way slabs. It's a little more than that. They're actually comprised of the easiest way to describe it is what's called a waffle system. Like if you ever have waffles, you know how you've got this square grid and there's these depressions? Well, that square grid sort of serves as the reinforcing ribs of the floor system. Like if you ever get the chance and you see what the actual floor system of the library looks like, it looks like this big waffle grid of reinforced concrete beams, and that's because it's designed in that two-way fashion. Again, two-way slabs are a lot stronger, but they're a little more complicated. One-way slabs, however, are pretty straightforward. The way that we design a one-way slab is, it's kind of like for those of you that have had geotech and you look at things like a retaining wall. Basically what you're doing is looking at a little slice of that retaining wall, and whatever's true for that slice is true across the board for the rest of the wall. It's pretty similar when you're looking at a slab. What we do is we cut out a fictitious 12-inch segment of that slab, and we assume that this is a rectangular beam. We pick out the reinforcement for this 12-inch slab, and then that's the reinforcement we use across the board. I have a design aid that I'm going to give you all next time that basically, instead of a number of bar chart like what you all have now where it's 4 number 8 bars, this is the area, it's basically a divided chart and asking, well, how many square inches per foot if we consider this bar spaced this far apart, and it's more appropriate for slab design. Whoops, excuse me. The one thing I'll point out is in addition to main reinforcing steel in slabs, because slabs are so darn thin, we have to include a little bit of steel for what we call it temperature steel. And the idea is that over time, concrete properties can change. They can undergo shrinkage. They can expand and contract due to temperature. And the idea is because that concrete is so thin, it has more of a tendency to undergo cracking than a beefy concrete beam. So we actually throw a little bit of extra steel in the slab solely to prevent that type of cracking. And the design of those are pretty straightforward. When we design slabs, we go back to this chart where we look at minimum thickness as a function of span length, and we use this to size the thickness of the slab. So think about it like this. If you know the thickness of the slab, right, and you know the width, if you're assuming 12 inches, then you already know what the cross-section of the beam looks like, and then all you have to do is select the steel. This is no different than the problem we just did, okay? Does that make sense? The only difference is you're selecting steel on a per foot basis as opposed to just 3 number bars in the whole, or 3 number 8 bars in the whole beam, or what have you. So the process is exactly the same, okay? We know what the cross-section looks like. The width of that beam is always going to be 12 inches. The height of that beam is just going to be the minimum height that we take from that table. We calculate an MN required, calculate a rho for design purposes since we know what the cross-section looks like. We choose a reinforcement pattern that meets spacing requirements and what have you. Keep in mind we have to choose main steel and temperature steel and then check accordingly. There's also a couple things on limits for tension temperature reinforcement. It's actually really simple. We'll get into that next time, and we're going to do a one-way slab next time. I do want to get into that because that is on your homework. Okay? But then after one-way slab design, that is everything on exam 1. Everybody good? All right, we'll see you next time.